webinar. So in poor form, I'm going to start with a disclaimer. The work that I'm going to present was actually commissioned by Reaxys, the Reaxys marketing team. So although the questions that I ask are overall about the perception and reality of information literacy in the undergraduate classroom, my answers are not always unbiased. Now, let me now tell you why I even got involved in this work in the first place. My second year in college, I found myself one day standing in the office of a research assistant, absolutely perplexed as he ripped apart a paper I had written, telling me that it was not a scientific manuscript and that I should go to Biosis for proper references. I was perplexed because I was absolutely clueless. I had no idea what he was talking about. I did not know what Biosis was. I had no idea what a scientific manuscript was. And it took the rest of my undergraduate career and the first years of my graduate training to eventually figure out how to find, read, and use scientific information. Later, as a professor, I saw the same perplexed look on the faces of my own students. Now, my excuse was that I'd never seen a scientific article before and I had never used an electronic database. But these kids, they had grown up with the internet. They had it on their cell phones. They had Google. I could not understand why there was this disparity between what I expected my students to be able to do with information and what they could actually deliver. So when Reaxys approached me about this problematic, I jumped at the opportunity to explore the question further. So what I want to accomplish today are three things. I first want to share some of the information or insights that I've learned from talking to people who face this problem every day in the classroom, faculty and librarians. And then I want to discuss the conclusions that we've arrived at about the way students interact with information based on these discussions and show that there's really a mismatch between how they use information and how scientific information is structured. Finally, what I want to do is bridge the gap between this use of information and the structure of scientific information, and for that I want to use a few examples of what Reaxys can do and how you can use it in the classroom to guide students towards scientific information structure. So first, some insights that we've managed to gather from talking to people. The best way to do this was basically to call up faculty, librarians, lab instructors, lecturers, and talk to them about their experiences every day in the classroom. To make sure that we reached as many people as possible, we ended up coattailing on a marketing campaign. And that campaign restricted a little bit who we could talk to, but we still ended up speaking to 19 librarians and over 100 faculty and lecturers from chemistry departments. We talked to people at undergraduate institutions primarily, so these are institutions that focus on undergraduate education. And for this initial part, we remained in the United States. We looked only at institutions in the US. Because this was part of a marketing campaign, we couldn't perform a systematic survey, but we had a very open discussion or opportunistic discussion with each caller about their experience in the undergraduate classroom. The one thing that we did attempt to ask every single time was which information systems did they use and when were those information systems introduced to students. And I've collated a little bit of the data here to show you what information systems come up very often. And there are three things that are worth noting on the left in the graph showing these information systems. The first is...
Anya,
yeah.
I don't think the slides have advanced. Can you refresh them?
So I should be looking at a slide titled which information system is used and when it is introduced?
Yeah, it's still showing information literacy.
Huh. How about now?
Okay, now we see a couple of people commented. Can somebody let me know if you can see that now in the comment? Yeah, okay, thank you.
Okay, I have no idea what happened there, but I'm glad that we solved it. Okay, so on the left is just bars showing the responses that we had from people that we spoke to regarding which information systems they used in the classroom. I should say that most people responded with multiple information systems, so they did not use only one. And there are a couple of things worth noting. The first thing is that SciFinder is very prevalent in the United States. We have now expanded this campaign to include mature, so Northern Europe, and the prevalence of SciFinder is not quite as dramatic as in the United States, but the spectrum of different tools that are used is definitely still the case in Europe. The other thing that is worth noting is that Reaxys is missing from this list, and that's not because Reaxys is not used in the educational setting. Quite the contrary, we have a number of customers that only use Reaxys in the classroom. But this was a marketing campaign, and we only called people who do not use Reaxys, and that's why it's not listed. On the right, you'll see sort of the proportion of callers that indicated that their information retrieval instruction happened in either lower division, upper division curricula, or about a fourth of them said that they were uncertain where it happened, or they had some very unorthodox formats for their curriculum that didn't fit into the category of lower division and upper division. What I mean by that is roughly half of the callers indicated that information retrieval was introduced in the first 2 years of an undergraduate journey, and 27% indicated that it happened in the last 2 years. Let's take a closer look at what these people said regarding the way that they introduced information retrieval. Those that indicated that it was introduced in lower division courses, the vast majority of them explained that it was introduced either in cursory, introductory workshops or courses with the intention of showing students what resources are available at their library. Alternatively, there might be a workshop led by a librarian, and that then happens either before a course or before beginning a particular semester. These two options have in common the fact that they are relatively generic introductions to information systems. There usually is no specific assignment goal behind them. They also indicated that very often instruction has to be repeated in upper division courses, and this is out of necessity because it appears that what students learned in these introductory courses wasn't retained until the upper division courses. One exception to that were students that are involved in research. Invariably, people indicated that students who did research learned information retrieval skills much better and retained that information much longer. Those that indicated that they taught information retrieval in upper division courses did so mostly on a need basis, where they had a particular research project for which they wanted students to be able to access background information, and they either instructed themselves how to use an information tool, or they had a librarian come in and teach the mechanics of an information tool. The reason they gave for why they do this in upper division levels is because instructing these tools is time-consuming and difficult, and they prefer to do it with students that have already declared chemistry as their major. Last but not least, we have a group of people that said they were uncertain when students were introduced to information retrieval, and that may be because they simply had an expectation that students upon arriving in upper division classes should have the skills, and indicated that they didn't. And another possibility was that information retrieval was a general curriculum that all students received at an institution, or as a multi-step introduction to library resources. What should be clear from this is that there is a broad spectrum of approaches to instructing information literacy and retrieval. In collating the information from all our discussions, we've learned a couple of things. One thing that we learned is that most educators believe that more can be done to teach information retrieval, especially in the science courses, especially in chemistry. Most also believe that information retrieval should be, or instruction on information retrieval should be incorporated earlier into the curriculum, but they indicate that this can be difficult to do because teaching chemistry information systems is time-consuming. It is hard to do early on when students perhaps have not accumulated the knowledge that they need about chemistry in general in order to understand what is happening. And they also indicate that even after instruction, students still tend to resort to what they call old habits. We'll talk about that in a second. Last but not least, instruction seems to be most successful with students that are doing research, which gives us an indication of the context in which they learn the best. So what we asked ourselves based on this is, first of all, what are these old habits that students fall back on? And what do students actually need to learn in order to do the type of information retrieval that is necessary to interact in a scientific curriculum or later on become a researcher? And how can we bring information retrieval earlier into the classroom? And last but not least, is there a way of mimicking this research student situation in the classroom so that students in the classroom outside of the context of a laboratory can also develop appropriate information retrieval skills? So let's start talking about the way that students deal with information. And I think that a quote from an interview with Dr. Gregory O'Neill at Western Washington University does a nice job of summarizing how students deal with information. He says, most students are savvy searchers. They find incredible things on the internet. However, they tend to be superficial or even impatient with their findings. If they can't find an answer within the first 20 hits, they stop. I think that this quote captures 4 really important features about how students these days interact with information. The first thing is that students have an expectation that information be immediately available to them. Now this is actually a positive thing. It's actually made Google an increasingly better search engine, but it actually prevents students from digging deeper into information. They've never had the incentive to dig deeper into information because it's right there at the tip of their fingers. Whoa, I don't know what happened there. The second thing that, the second feature that we can collate from this quote is that students have grown up with having information at their fingertips, so information is very easy to find. The upshot of this is that the relevance of a source has become secondary to the availability of information. So they spend less time actually evaluating a source since it's so easy to find information in the first place. The third thing is that students want direct answers, and they expect usually a single truth, a single answer, which means that when they do get multiple answers, and especially discordant answers, they don't really know how to process that. Last but not least, most students assume that a search engine understands them. This means that they're not versed in building search strategies. They don't know how to take a research question, break it down into individual components that they can use then to build a search strategy. The result of this is that the way that students interact with information or deal with information is at a mismatch with the structure of scientific information. Science builds on the work of others, which means that digging deeper, following the reference trail, is sort of a staple of scientific research, just as much as assessing the value and the appropriateness of information that comes in a source. Furthermore, science advances because of multiple and disparate answers. And learning to explain differences in answers is really part of what a scientist does. So it really shouldn't be surprising that when students are asked to retrieve scientific information, background information, they end up delivering poor results, which this causes frustration not only to the students, but of course to educators who have to deal with those poor results. And ultimately, this means that student learning outcomes are not achieved. Given this mismatch between how students use information and how scientific information is structured, and the very high likelihood that most students encounter scientific literature for the very first time at university, I have to ask myself why it is that we think that students can process a list of references. It seems to me that above and beyond showing students how to use an information tool, we as educators need to guide their transformation from being a student to being a scientist. And this really entails sort of creating opportunities in which students can revamp the way that they approach finding information and using information. In the next few slides, I'd like to show you a few examples of what I mean guiding this transformation and how you can use Reaxys to address these 4 features of the way students interact with information. So I'm going to go back to this list of 4 features, and we're going to look at each one of those in reverse order. We'll start with number 4, and I'll show you some ways that perhaps Reaxys can contribute to overcoming that limitation in the way students interact with information. So we talked about how students assume that a search engine understands them, and the result of that is that they are usually not versed in building search strategies. Dealing with this, you can either give them a search engine that understands them, or you can teach them how to build search strategies, or a better option is to do both. And the reason why I think that this is a better option is because if you do give them a search engine that understands them, students can start earlier searching for information, regardless of their experience or lack thereof in using electronic databases. Then, as they advance through their training, they can do increasingly sophisticated searches as they learn how to build proper search strategies. I find Ask Reaxys to be a particularly useful tool to this end. So Ask Reaxys is a pretty prominent feature in Reaxys. It's a Google-like search box at the top of the screen where you can enter a phrase, something like esterification of benzoic acid. And when you click search, Reaxys delivers relatively quickly, in this case, 86 reactions. What Ask Reaxys has done here is it's interpreted natural language, esterification of benzoic acid, and it automatically recognizes what the search intention is. In this particular case, it's decided that you're looking for reactions, and it delivers those results directly. So Ask Reaxys is a very nice tool for very quick searches. You just have to find something very quickly. But I think it's also an outstanding entry point for students who have no experience using databases, no experience breaking down research questions, where they can simply enter a phrase and find results, useful results, relevant results. Ask Reaxys, though, does a little bit more than just being like the chemistry version of Google. Ask Reaxys also supports learning. So after you've done a search in Ask Reaxys, in the breadcrumbs trail in Reaxys, you can click on Show Query, and what you get is an analysis of how Ask Reaxys has interpreted and performed a search based on what you entered in the entry field. As you can see in the box, the analysis shows 2 separate queries. The first one delivers 86 reactions in Reaxys, and the second one delivers 588 citations in Reaxys. The colors on the search terms indicate how Ask Reaxys has interpreted these search terms. In this case, esterification has been interpreted as a concept and benzoic acid as a compound. And the word "of" is a critical keyword because it ultimately tells Reaxys that what you're looking for is reactions, a specific type of reaction where benzoic acid is the starting material. Listed underneath that is how Ask Reaxys ultimately retrieves the results that you're looking for and in what context it does so. So Reaxys operates in 3 different contexts. One is reactions, the other one is substances, and the last one is citations or document records. And in this case, it's operated in the context of reactions. It's searched for benzoic acid as a starting material, performing a structure search, and it's allowed for the exact structure to be used as well as perhaps radicals or other forms of benzoic acid in the search. And it's combined that search with reaction type, specifically esterification and the plural form esterifications. And you can see that in the description below of, apologies, I don't know how this is happening. So you have now, students have now a very clear idea of how Ask Reaxys interprets their search phrase, which teaches them also how they can break down research questions into individual search components. And it also shows them very clearly how it goes about retrieving results. This is a pretty important part of Reaxys because Reaxys builds on Querylets, which are used ultimately to search for information in specific database fields. So the components of research questions can be mapped to data fields in Reaxys, and then each one of those data fields corresponds to a search unit, which we call Querylets. And that brings us to the next aspect in which Reaxys can support student learning, which is in helping them break down a research question. So let's say a student is assigned to identify an unknown compound. This compound happens to have antimicrobial properties and was isolated from a natural product. And the student did some work in the lab, and the results from his or her work indicate that the substance has 30 carbon atoms and has an optical rotation of 75 to 85 degrees. We can break down this information into search components. And the first thing that we know is that the compound has 30 carbon atoms, and we can find a querylet, in particular the molecular formula querylet, where we can enter that information so Reaxys knows that that information should be searched for. Here we've entered C30 with an asterisk. That means that there are 30 carbon atoms, and the asterisk is a truncation indicating that this is a partial formula. So those 30 atoms can be in the molecule with other elements. The second thing that we know is that the optical rotation of this compound is 75 to 85 degrees. And there is a querylet for optical rotatory power where you can enter a range or a specific value, or you can say greater than a particular value. The third thing we know is that it was isolated from a natural product. There is a querylet specific for the isolation from natural products. So you can say, if you click exists, it knows to search for products that were, for compounds that were isolated from natural products. And then we know that it has antimicrobial properties. And if we don't know exactly what querylet we can use in order to search for that, Reaxys has 3 very powerful querylets called the basic indexes, one of which is the substance basic index. And there I can enter antimicrobial. And what the querylet will do is actually search for this term in all the data fields of a substance record. If I need to learn more, if I want to expand my search, if I want to find out what terms might be useful for this particular search, I can click on Lookup, and I will get a list of keywords that are relevant to this particular search. And I might choose some synonyms that I hadn't thought of, like antimicrobic or antimicrobial, and transfer them also to my search so that they're included. Now I have a search strategy. All the information that I knew about my compound has been entered into particular querylets. And what Reaxys will do is combine those querylets to retrieve information, to retrieve records of substances that have those properties. So you can see that by using Reaxys, students learn to break down the research question, and they're also supported in finding potentially relevant synonyms or other terms that help narrow down or optimize a search. And we'll look at the results, at least one of the answers to this search a little later on. So the next item on our list, the next feature on our list was that students want direct answers, and they usually don't expect to get multiple answers, let alone discordant answers. And I think that the only solution to this problem is to give them real-world data and give them the opportunity to make sense of data variability. And here I think a really excellent way of doing that is by taking advantage of the excerpted data that's included in Reaxys. And the reason why I think that this is particularly powerful in Reaxys is because of the way that this information is displayed. If we go back to our search, one of the results is this acid, and we've pulled up here the substance, one of the substance records that results from the search. And the very first thing that you'll notice is that under the hit data are listed the actual data that we had, the actual terms that we had searched in our query. If we click on the optical rotatory power, Reaxys delivers tabulated data of 60 optical rotation measurements listed with experimental details and references. Let me show you a close-up of that. So you can see in the first column we have the type of measurement done. In the second column we have the concentration at which the measurement was done. In the third column is the solvent used for the measurement. Then comes the actual measurement itself, highlighted in blue because it's a hit term. Then we have the wavelength at which the measurement was done, and ultimately the temperature at which it was done. Students can then use these excerpted data to really explore how experimental details or experimental conditions impact results, as well as maybe perhaps select references that use the same conditions that they have available in lab so that they can perform the measurements themselves. So this gives them hands-on information or data that they can use to explore variation and try and get a better understanding for why there are multiple answers to a question. The next feature that we talked about is that information today is very easy to find. It's on their cell phones, and because of this, students haven't had the incentive to explore the relevance of a source, where the relevance of a source has become pretty much secondary to the availability of information. And I think that this is a very critical aspect of learning how to become a scientist, and one that is often overlooked. And it's really the job of an educator to show students how to assess the relevance of a source document, and in many ways to help them glance into the content of a source so that they can assess whether they should read a particular reference, whether the information included in that reference is appropriate for their particular research question. So anything that helps students make these assessments is going to further their interest in pursuing further the information that they've found. And Reaxys has document records that I think are particularly interesting because they contain a massive amount of information that you can use to explore your findings further. Interestingly, the literature repository of Reaxys, which is very extensive, is highly underutilized. Let me show you a little bit about what I mean in these document records. Going back to our search, if we choose one of the results on optical rotation, we can look at the reference provided, and for example, we can click on one of the authors, and what Reaxys will do is interact with Scopus, and it can deliver then statistics about the publication record of that author. What that means is that it allows students to evaluate the reference by assessing the expertise of the authors. What is it that they do? What other publications do they have? Do they seem to be cited very often, especially in this particular topic? Clicking on View Citing Articles also grants access to Scopus, but here in viewing how this particular reference is cited in other articles. We get a list of other articles that cite that particular document. Here students can assess the value of this particular reference within the context of the literature landscape. What is it about the reference that is important? How is it used in other publications? How is it cited in other publications? What do these other publications address? What do they talk about? What are their topics? This gives them really a much better view of whether this reference is important to them than just the reference itself. We can also click on Show Details, and Reaxys will take us to the document record of that particular citation. What's nice about these document records is that they can list also specific content contained in that article. In this particular instance, it lists that there are 12 substances described in this article. And if you click on that link, those substances are displayed in small snippets that ultimately take you to substance records where you can see the structure and the identifiers of those compounds, but also a very extensive, for each one of them, a very extensive list of properties that might be of interest as a student explores further and deeper into compounds that through this reference are relevant to the search that he or she performed. Ultimately, these document records allow a student or give them paths to explore more and to assess the source document and decide whether it's relevant to their original research question by showing them, giving them a glance of what's inside that reference and linking them to other aspects or other records within Reaxys that are related. The last feature that we spoke about was that students expect information immediacy. That means they expect information to be at the tip of their fingers, and ultimately this leads them to not be incentivized to dig deeper. Here I think the issue is to trigger interest in digging deeper, and that's what we need to do, and the best way to do that is to show them how to make novel connections. How do I take information that I have and look for how it relates to other contexts, for example. I think that the highly interlinked information in a Reaxys document record really supports this kind of exploration and digging deeper, but there's something else that I want to show you. Document records in Reaxys are extensively indexed. If we go back to that document record that we were looking at earlier, and click on title and abstract, we get the title, we get the abstract, but I want to draw your attention to the keywords down here. We have the keywords provided by the author in the actual publication. We also have keywords that come from Reaxys itself. These are index keywords assigned to the article based on the very extensive taxonomies of Reaxys. But we also have keywords from Emtree. Emtree is the very extensive taxonomy that underlies Embase, a leading biomedical information system. Additionally, we also have keywords from Medline, also a biomedical and life sciences information system. So these keywords allow a student to find new search terms which might help him or her expand or optimize his search. And it also allows them to view the relevance of this particular reference within the context of other conceptual frameworks, in this case biology. And this indexing is not limited to biomedicine and life sciences. This is another document record in Reaxys, and as you can see, under the keywords, we have keywords from Compendex, which is a technology and engineering database. We have, again, Embase. GeoBase is another leading database that focuses on geosciences and environment. We also have indexing terms from GeoBase. And we have very extensive indexing from Reaxys, from the Reaxys taxonomies, not only in terms of chemistry. We also have indexing about the geography relevant to the particular citation, about the species relevant to the particular citation, and Reaxys also has a very nice indexing for trade names of drugs. So you can see that with this full spectrum of keywords, students have access to a sort of a six-dimensional view of chemistry and how chemistry applies to other disciplines or transcends disciplinary boundaries. Now, all in all, Reaxys has a wealth of tools that I think can really help support guiding students in their transformation from being a student, from being an information user that has expectations of immediacy, that doesn't dig particularly deep, to being a scientist, someone who follows the reference trail, someone that digs deeper, someone that builds on the work of others. But very important to add to this is that none of this really works without you, without the educator. And what I mean by that is not necessarily that an educator should be responsible for teaching the mechanics of an information tool. Quite frankly, I think that we've gotten to the point where we can expect an information tool to support the educator and not the other way around. No, I think educators, their job really is to create a need that drives students to the right information system. And I think that this is best done through concrete, very clear assignments, graded better. And these assignments need to provide a genuine, concrete context for why a student should use an information tool. It should be connected to the particular topic that's being discussed in class. It should be very clear to a student why the information tool or the information system will contribute to their ability to complete this assignment. In order to do that, assignments need to have very clear expectations. I think it's very important to be explicit about what a student should do and learn from an assignment. So if you want students to actually read references, then it should be clear in the assignment that that is an expectation, and there should be concrete activities for that reading. Ultimately, I think that guiding students in their transformation to students is all about teaching them not how to find information, but how to use information. And I really think that Reaxys can help, on the one hand, because it makes it easier to find information, because it accommodates a broad spectrum of experience with electronic databases, because it has very sophisticated tools that are relatively easy to use in order to find information, but also because it's a very transparent system. It allows you to really see how Reaxys goes about extracting information or retrieving answers to your research question. I hope that I've managed to show you at least very quickly how Reaxys, or some of the features in Reaxys that can be used in the classroom to further information retrieval skills. But if you want to learn more about our thoughts regarding chemistry education, our thoughts about how Reaxys can be used in the classroom, and by this I mean not only assignments for students but also in preparing lectures, please do visit our dedicated website that we're building, in the process of building. We're always adding new tools. For example, we have, you can see over here, we have case studies. These are Reaxys users that implement Reaxys in the classroom and share their experiences, discuss how they go about using Reaxys, discuss what the results are, how students perceive Reaxys, and what their goals were for including Reaxys in their work in the first place. We also have what we call tool sheets, which show step-by-step how to use Reaxys for particular types of searches, or step-by-step how to use Reaxys to pull data that can support particular lecture types. And we're always very interested in hearing from people who use Reaxys or who want to use Reaxys but don't know exactly how to go about doing so. Please do contact us, and hopefully we can support you. Hopefully we can give you some guidelines, and maybe you can give us some guidelines on what new tools we should make available or what supporting documents we can make available to make your job easier. And with that, I'm hoping that we can open up session for questions. I'm looking forward to hearing from you. I'm looking forward to seeing your questions, and thank you for your time.
That was excellent. Thank you. If anyone has any questions, you can type them into the question pane. We have a thank you. And give it a few moments to see if anyone has any questions. You're getting several thank yous, though. I think it was a very good webinar. Okay. If anyone has any questions, you can always submit them later, and we'll be happy to answer those. That would be an excellent webinar, and we will send you a link to the recording and a download for the slides. And thank you all for attending.
Thank you.